So let's see how some of these ideas can be applied. We're given a velocity vector of a particle moving in the plane, and we know that when t equals 0, its position is 4, 7. So the first thing we're asked is to find the position of the particle at time t equal to 2. And before we do that, let's just get the actual position vector. And this will combine some good ideas that you'll hopefully have internalized in calculus at this point. So your position is always going to be where you started plus how you've changed. So we can take this component by component. Where is your particle initially? It's at 4. And how does its position change? Well, if you integrate velocity, that will give you a change in position. So at t equals 0, it's at 4. So how does it change on the interval 0 to t? Well, we're just going to put the velocity. I need to use a different variable in here. But that right there gives you the exact position at any time t of your of the x coordinate of your particle. Right, and it'll give you the change in the the position of your particle, at least the x coordinate part. And then its the y coordinate is where it started at t equals 0, 7, plus how it changed on the interval 0 to whatever time value we're interested in. And so now I've got my position as a vector. And I can plug, I asked the position at t equals 2, but I could ask it at any given time now. All right, so again, we're basically applying the concept of position in one dimension, but we're just doing it per component. And so the position at time t equals 2, we don't need our calculator for these, but I'm gonna use them anyway. So this is 4 plus the integral from 0 to 2 of, and now we could put a t in this spot if we had to, but I'm just gonna continue with x. So it's that integral. All right, and so then taking out our calculator, I put x cubed minus 3x squared into y1. I put in 1 plus sine of pi x into y2, and then I use the integrate function on the calculator, and I got that this integral here was -4, and that this integral here was 2. So this ends up being 4 minus 4, comma 7 plus 2, or in other words, 0, comma 9. So we know that when t equals 2, that this particle is at the location 0, 9. The next question says to calculate the total distance traveled by the particle on the time interval 0 to 4. Well, we know that the distance traveled is just the integral on the time interval 0 to 4 of the square root of my velocity, the components of my velocity function squared. Right. This, again, if you think more notationally, t cubed minus 3t squared is just dx dt, where x of t is the x component of our position vector. But in any case, all right, so here's where I would probably, in order to do this, what I would do is I'd put this, because this is definitely a calculator problem, I'd put this into y1, I'd put this into y2, and then in y3, this is just how I like to do it, so I don't have to type so much into one equation. I put the square root of y1 squared plus y2 squared. And so again, when I say put this into y1 and y2, I'm not including the squares. So doing that now will get me let's see. I'm sure the suspense is just killing you. So I integrated on the interval 0 to 4. This integral here, it's taken a little while. I got 15.28. Or 2.8 even if you round to thousandths. Alright, so that's the distance traveled. And the next question said, what is the speed of the particle when t equals 2? Well, when t equals 2, in order to get the speed, we need to know its velocity vector. So v of 2 is nothing other than 2 cubed minus 3 times 2 squared, comma, 1 plus sine of 2 pi times 1. But that ends up just being 8 minus 12, which is negative 4. And the y component becomes 1. And so my speed is just going to be the magnitude of my velocity vector, which is the square root of negative 4 squared plus 1 squared, which is the square root of 17. And so now I know how fast it's going right at that instance. Alright, so here we have the position of the particle as a function and then at a particular point. We've got the total distance traveled with the help of our calculator, and then we know the speed of the particle at any given time.